Welcome to Webinar Wednesday. Today is our March webinar. Yes, it is April, but it's our March webinar. So we'll just go with it. My name is Kelly Huff. I am the marketing manager at Veritech Solutions, and our presenter is Dan Hahne, the director of High-Performance HVAC Solutions with Veritech. This is our 2025 education schedule. Our April webinar is going to be in April, and it will be designing and controlling a medium pressure VAV system. There's the rest of our dates. We have an educational resource library on our website where all of our past webinars live, the recordings, and I'm actually in the process of updating this to a new and improved website, so stay tuned for that. We just sent out our quarterly newsletter last night. We'll be doing our monthly newsletters, and then every quarter we'll do a bigger one that has even more information. So if you're getting our emails, you probably saw this. If you are not sure how you're here, maybe somebody shared this webinar with you. If you want to get onto that email blast, please let me know. So a few housekeeping items before we get started. We are recording this session. As I said, I will share the video after we're done here. If you have any questions throughout the webinar, go ahead and pop them in the chat, and we'll go over them at the end. If you need PDH credits or AIA, make sure that your name is displayed correctly in here so that I can make sure to get you checked in, and I'll get you your certificate. We did get this AIA approved, so that wasn't on the registration. So if you do need an AIA credit, please make sure that you send me a message in here as well. While I have that up, if you haven't already, you can scan that QR code and follow us on all of our social media channels and stay up to date with all of the latest events and educational opportunities, as well as the emails. Dan Hahne is our professor today, Professor Hahne. He has a wealth of experience within our industry, almost 40 years, and he is our high-performance HVAC solutions and our educator. He is very active within the ASHRAE community. Most notably, recently, he has been named an ASHRAE Distinguished Lecturer. So he's getting to present all around the world with some of these topics. He also has had several publications in ES Magazine, with one just recently this February. So with that, Dan, I will turn it over to you.
Thank you, Kelly, and thank you all of you for joining us today on today's presentation of ASHRAE Guideline 36/2024, High Performance Sequences of Operation for HVAC Systems. This, unlike a standard, is actually a guideline. So it really is written to help support our engineering community, and in this respect, with regard to building controls, also facilities groups, controls contractors, or whatever. And the goal that controls sequences can be written in a way that they become more standardized and more accessible by all parties in actually implementing sequences to effectively operate and manage building mechanical MEP systems. I do have a special acknowledgement today for Siemens. They've been a deep resource in helping to support the formulation of this presentation, and I've drawn from them on a number of occasions. And I especially want to extend a thank you to Will Podgorski, Jim Coogan, and Ryan Sue. Today's agenda is we're going to cover a number of aspects about controls. We're going to look at building automation systems, a building central nervous system. We're going to propose an argument that the control system acts like the human nervous system in actually controlling the operation of our own physical bodies. We're going to look at a history of Guideline 36, what brought it about, what inspired it, what were the advantages of formulating it. We're going to look at the actual guideline itself. We're going to review its text in the forward purpose and scope. Then we're going to look at set points, design and field determined conditions that sequences of operation will adopt or should adopt in order to maintain thermal comfort and indoor air quality within a building efficiently. We're going to just briefly touch on the hardwire points offered by the guideline for VAV terminal units, fan-powered terminal units, dual duct boxes, air handlers, etc. We're only going to just reference it. We don't have time to go through all of the pieces of equipment and prescribed hardwired points. Then we're going to look at the sequences of operations themselves, do a scan through the document, try to hit on some salient points because it really is somewhat of a technical deep dive. Then we'll close with the future of the guideline and concluding remarks. So building automation systems, a building's central nervous system. Buildings I would like to offer, and I know I've heard it before, I have not think of this. Buildings are dynamic living structures. They are not merely static enclosures that we pound mechanical systems into so that we have air flowing when a thermostat says enable. Buildings expand, they contract, they vibrate with ground vibration, they exhale, inhale, depending on building pressure, whether it's positive or negative, and buildings shift with the moving ground. An HVAC system, you could say, is a building's cardiovascular system. HVAC systems supply vital air throughout a building. Why? To promote thermal comfort and to create, hopefully, healthier environments, though we're seeing more and more that really is not the case. Air, water, and refrigerant are energy transfer mediums. You maintain thermal comfort in a building by moving energy. And in order to move that energy, you have to consume energy in the form of kW to move thermal energy in the form of BTUs. So if we look at the human body, how does the human body move blood and nutrients throughout our body so it can sustain itself and operate at the appropriate condition we seek for it to achieve? Blood flow rates vary depending on physical activity and metabolic rates. HVAC systems also, they regulate building energy transfer by applying controlled technologies, sensors and program controllers to condition buildings. So what regulates blood flow? Demand. If you have very active areas of your body, like a baton twirler, they're probably getting more blood flow to the arm than maybe to more static parts of their body, maybe their feet or whatever. Demand or physical work is a complex interplay of mechanisms and the body's response to various stimuli like hormones and nerve signals. Physical work increases blood flow to active body region. When a body is at rest, blood flow decreases. So blood flow mechanisms are monitored and efficiently controlled by the nervous system within very, very close tolerances. HVAC systems act like a body's cardiovascular system when it regulates blood flow rates. HVAC systems condition and regulate airflow to and from buildings to meet heating and cooling demands. There are other human regulatory agents like the human will, a fun topic to discuss. We won't have time today to do that, needless to say. But anyway, HVAC systems, controlled and how. HVAC systems are controlled by a building automation system, also known as building management systems and building energy management systems. Sensors in a building monitor a building and the outdoor air conditions and send inputs to program controllers so the controllers can calculate and send out outputs. The BAS acts like a building's central nervous system, sensing and controlling fluid motion, air, water, and refrigerant, which are the heat transfer mediums in a building. So again, the primary objective historically of an HVAC system is to maintain building thermal comfort and to provide indoor air quality. So today's objective in the writing of Guideline 36 is to provide thermal comfort and indoor air quality efficiently. And in order to do that, we have to have sequences of operation that are structured in a manner to allow for efficient heat transfer. So how does it do that? An HVAC system needs to be designed to consume only the amount of energy in the form of kW required to move energy in the form of BTUs to or from a building at any given time of day and at any given time of year to maintain building set point conditions. So let's look at the history of Guideline 36 and why and how it came about. Before we do that, let's give the guideline a little bit of context. I love history, quite frankly, and I was rather surprised to learn that the ancient Persians, 4,000 years ago, actually had their own forms of HVAC or ventilating systems. They used passive air movement in the form of wind, and they would create architectural structures that would capture wind and channel that air, that wind-forced air into a building to provide ventilation and allow the natural convective forces of air to warm within the building and to exit the building through thermal buoyancy. So you had a continual flow of air through the space. There was no mechanical work to do that. It just happened by nature. The problem is with that design that though effective when the wind was blowing, at least up to a certain level, there was no control. You got what you got. System airflow was dependent on the environmental conditions, wind velocity and direction, and the wind catcher free area available to the wind, as well as outdoor psychrometric conditions. So the first pass of HVAC systems exploited the natural forces of physics and properties by capturing and channeling wind and exploiting variations of air pressure. They exploited physical forces of equilibrium, such as convection and radiation, and also the convective stack effect that can occur within a building where warm air rises and cold air falls. The first active HVAC system where there was mechanical work applied and kW consumed occurred in 1882 when Dr. Schuyler Wheeler invented the first electric two-bladed fan. The problem is the fan was on-off. So did the fan have control effectively? It did. You either wanted the fan on or you wanted the fan off, but it wasn't very tight control. Old HVAC systems were constant volume. They were on-off. The first DX unit installed was in 1931, and it was a window unit that fit on a window ledge. The first split DX unit was built in 1932, but the fan, motor, drive, and blower were all constant speed. When the unit was on, the air blew at a constant rate, and also the compressor came on to cool the air as well, and when the unit was turned off, the compressor and fan turned off. So constant volume systems offered some challenges. To effectively condition a building with various loads at various times of day at various parts of a building, you required a number of different air handlers to make sure each area or group of zones were adequately conditioned. Fans ran continuously at constant speed, so there was a lack of temperature and humidity control, and often poor ventilation, certainly when thermostats were met and units were shut off. So constant volume systems are very inefficient. You get what you get when they're on, and you don't get anything when they're off. that provide thermal comfort challenges and poor indoor air quality. So how do we design a more efficient HVAC system? Reduce or eliminate start-stop control and cycling. Regulate zone heat transfer medium flow, like blood flow in the human body, at appropriate conditions to offset thermal energy and humidity gained or lost. Objective then is to consume only the amount of energy necessary to do that. Well, in order to control heat transfer, you have to monitor. You have to monitor flow and temperature. You need to monitor the temperature of the space that could require cooling or heating, and you have to monitor the flow of heat transfer medium to those spaces so you don't overcool or undercool or overheat and underheat the zone. So to regulate supply air, water, and refrigerant conditions and flow rates, monitoring space and heat transfer medium conditions is required. Fluid flow rates are regulated by varying fan motor RPM, or fan motor speeds, and compressor rotor or scroll rotational speeds. Regulating air, water, and refrigerant flow rates and conditions conserves energy because you can now use only the work necessary to provide the heat transfer medium needed to discretely satisfy loads, whether they're at low load or high load. So low load conditions result in low flow rates, high load conditions result in increased flow rates. And a high efficiency HVAC system needs to provide tighter control to do this efficiently. The old control systems were pneumatic controls. They're still in existence in a number of old buildings today. They were the earliest form of control, and they were installed actually in the early 1900s. Pneumatic control systems used compressorized air in the regulation of air to open and close actuators and devices. But they had some inherent problems. One, they had a limited range of proportional control and response. They were hard to maintain, keeping pneumatic lines free of debris. They were slow to act and had delayed system response time, were very inefficient, and they needed to be calibrated. Direct digital controls, or DDC controls, entered the market in the 1980s. Direct digital control advantages were these. They offered precise temperature and humidity control and monitoring, greater energy efficiency because they offered tighter control, real-time monitoring and adjustment, automated scheduling, remote monitoring from off-building site, reduced downtime and maintenance, etc., etc. So DDC control systems function and operation provided tighter HVAC control for more efficient operation. Well, what defines the actual operation of a DDC control system? Sequences of operation. A sequence of operation describes the way the equipment in the building responds dynamically to changing demands. Sequences of operation, however, are normally custom written per building. Engineers accumulate various sequences from previous buildings and they apply them onto new designs with some customization in order to perhaps allow that sequence to more appropriately fit the design requirements. Design teams, however, often simplify sequences, allowing systems to be more accessible to service and facility techs. Facility technicians, however, also often override sequences of operation and controls within a building. But simplified systems are not tightly controlled, efficient systems. Custom SOOs that are not consistent result in a reduction of building efficiency and prolonged startup and commissioning time due to confusion between the specifier, the installing control contractors, the building technicians, and the commissioning agents. So reduced control also in a building can result in non-compliance with industry standards, such as ASHRAE Standard 90.1 and ASHRAE's ventilation standard 62.1. So reduced control results in reduced ventilation rates and indoor quality. So the challenges with simplified controls is oversimplified sequences are not always well programmed, debugged, and commissioned. They were written for one-off custom applications, resulting in subpar building and performance historically. Each building is uniquely controlled based on the design team experience level, type of building, quality of startup, and level of commissioning, and the capability of the service techs who actually work on that building. So Guideline 36 was actually born out of ASHRAE Technical Committee 1.4, which specializes on control theory and application. And it was written out of 1.4 to promote industry consistency of building control and operation for improved efficiency in indoor air quality. And I can't help but think what also drove it was ASHRAE's commitment to decarbonization and for creating healthier environments. So the guideline was created to provide best-in-class control sequences to optimize that have been optimized to minimize energy use, maximize thermal comfort, and maximize IAQ. And the sequences are intended to be pre-programmed and pre-debugged by control system manufacturers so their controllers can adopt the sequences more readily and effectively, and to create perhaps less of a divide between the various controls manufacturers and their controlled solutions for buildings. So the actual guideline originated, the original guideline committee meeting occurred in 2014, and the first guideline was written and published in 2018, and it focused on medium pressure VAV systems, VAV terminal units, and air handlers. Guideline 36/2021 offers language to chill water central plants, hot water plants, and fan coil systems. And this guideline will be advancing in the future towards 100% outside air systems, active and passive chill beams, passive radiant cooling and heating systems, and pressurized laboratories. So the early results of implementing some of the sequences recommended by the developmental stages of the guideline saw some rather interesting results. There were dramatic energy savings achieved in a boiler system in 2 buildings, 50% greater efficiency. Maintaining code minimum ventilation requirements occurred in buildings. Improving thermal comfort because you had tighter response in providing the conditioned air in the volume necessary to maintain set points at thermostats. The guideline's early results had some challenges, though, because the guideline, though it benefits everybody in the building and design and construction process by providing a commonality of language, engineers were reluctant to specify the sequences because they are complex, and they are. It's a deep dive. And control contractors will not implement Guideline 36 sequences unless they are specified. So let's look at the guideline itself. Let's begin by making sure we understand more fully what its purpose is. So in the foreword of the guideline, it goes on to say that the guideline establishes a set of standardized advanced sequences of operation for common HVAC systems to reduce engineering time, reduce programming and commissioning time, reduce energy consumption by making systems less dependent on poor implementation, and reduced energy consumption by ensuring that proven cost-effective strategies are fully implemented. They can also improve indoor air quality by ensuring control sequences are in compliance with IAQ standards, specifically 62.1, and municipal local codes. Reduce system downtime, including diagnostic software to detect and diagnose systems, is a benefit for an owner because with controls capability today, having fault detection in a system and predictive maintenance can send alarms out on MEP systems, on pieces of equipment that are tending to go out of performance, and consequently they can be serviced before there's catastrophic failure. So having this fault detection and predictive maintenance capability written in is a very positive aspect of the guideline. So again, to repeat, the purpose of the guideline is to provide uniform sequences of operation for heating, ventilating, and air conditioning systems that are intended to maximize HVAC system energy efficiency and performance, provide control stability, and allow for real-time fault detection and diagnostics. The scope provides detailed sequences of operation for HVAC systems, as well as functional tests that can be executed by commissioning agents and controls contractors during startup and commissioning. So there's commonality of language to allow for a more efficient startup period. Who is the intended audience? HVAC designers, control contractors, commissioning agents, building owners, and a common formatted sequence of operation will in time facilitate improved expression of the design intent. So specifying engineers, controls contractors, and commissioning agents will speak standardized language of sequences over time that will facilitate the future of sequence writing. The guideline was actually written in a manner and formatted so that the sequences proposed can be directly copied and put on mechanical drawings. I saw it recently on a Smith Group project for the U of A, where they actually referenced on the drawings a scrutinized review of Guideline 36 and provided the language right on the drawings, which is part of the guideline's intent. Control manufacturers can now develop products that are more readily conducive to promoting the sequences the guideline calls out. Control contractors can more appropriately apply the solutions and wisdom of the guideline, and commissioning agents more effectively execute a common format of testing. So the way sequences actually develop in the pre-design phase is actually starts with the specifier. The BAS specifier will be the primary user of the guideline, and he has to come up with an actual product, a sequence of operation that is to be given not only to the controls contractor, but also to the commissioning agent. Then the controls contractor takes the project sequence and then brings their own wisdom and experience in evaluating those sequences, and then have some margin of flexibility to influence that sequence that is then submitted on for reevaluation by the engineer. And that engineer evaluates the submittal document and then lists any objections or approvals or edits or markups before that document is actually approved and given back to the controls contractor for the contractor to write into code and to put into the actual controllers within a building design. So that's the way the actual flow of the process goes. And all of it is to provide a more integrated system approach with everybody speaking a more common form of language. So Siemens shared in one of their videos how they've seen implementation of the guideline in actual documents. There's method 1, which is one general reference to comply with Guideline 36 on drawings. You literally just write that on the drawings. It's the easiest approach for the design engineer. Doesn't take them any time, but the specifier does not write a sequence that contractors and building owners can use. The contractors and building owners and commissioning agents have to cipher through all of the guideline to have their own interpretation of what they mean. So that could add confusion during startup and commissioning. And the approach, however, the approach may become practical in the years ahead as the guideline is more widely adopted, and there'll be a common inference of understanding of what the sequences are when Guideline 36 is referenced in relation to a VAV system, a chill beam system, etc. Method number 2 is including a large portion of the guideline on the text, where most of the guideline text written is to be directly inserted into the contract documents through cutting and pasting. The standalone project specification results, however, there are some guidance references and directions in the guideline, and in the directions it can be contradictory at times, and a design specifier has to decide what they are going to do with regard to the available language. And so if you just do if a specifier just does a direct copy of the language, it's going to result in confusion, and it appears that they didn't actually do their job as effectively as they could have done. Another method is where smaller sections are discretely cut out that address specific sequences for a specific design concept. Again, this can be cut and pasted, but it keeps the specifier in the actual creative sequence writing mode. And consequently, their system will more likely perform directly to the design intent of the guideline and reduce perhaps improper interpretations from the installing contractor or the commissioning agent. And then what we'll probably see more in the future are multiple references to numbered sections that actually addresses section numbers to provide the language of how a piece of equipment is to operate under given conditions. The guideline provides direction and guidance and other additional information. The directions are in bold, black font, and the guidances are actually in italicized, non-bold, regular font. So consequently, when you look at the guideline and you take into consideration the directions and the guidance clauses, as well as the varying types of VAV systems, chances are, if it's applied on a medium pressure VAV system, only 20 to 25% of the document will actually be used. So it can be a little daunting to look at over 300 pages of sequences, but once your system is defined, it really does narrow what it is that you'll be looking at. So let's look at Section 3 of the guideline, set points, design, and field determined. So what is the driver of the controls engine? What actually drives the whole system? It's the sensor. It's the thermostat. The sensor actually measures the amount of thermal energy in the space, or the volume of airflow rate actually being supplied to a space. And the total load read by the thermostat and other sensors, such as relative humidity sensors and perhaps maybe even CO2 sensors, is the sum of all zone loads in the space, as well as the actual load inherent in the outdoor condition. HVAC systems respond and operate in respect of zone and sensor readings, and consequently send inputs into controllers for them to respond. So how a system responds is a function of controllers used and sequences of operation that directs how those controllers will operate under the given conditions as monitored and sensed. What's rather interesting about the guideline is that its actual written structure somewhat mimics and mirrors the structure of an MEP system designed within a building. So let's evaluate this a little more closely. Let's look at room and segment data structures in a room. The first objective is to control thermal comfort and indoor air quality in a room. And you have an HVAC application in the room. And that HVAC application has all sorts of assigned values as set points, outdoor air conditions, schedules that go on at the building energy, at the BAS, at the building automation level, or perhaps at an air handler controller, and that is actually exchanging data with the controller serving the room. Then in section 5 of Guideline 36, there's a review of generic ventilation zones and generic thermal zones that are defined, and we'll cover those terms more closely in a little while. All of this information is given to the zone, and that is called a zone group. A zone group is comprised of a group of zones served by a common air handler. Also within that space, in a VAV system certainly, and the logic applies as well to fan coil units, chill beams, fan power terminal units, is the actual device, the HVAC device that is responding to the local load and making the adjustments it needs to maintain the conditions that are called out in the room designations shown on the left. So all of this is interconnected and data is exchanged not only from the VAV terminal with the amount of airflow going through the terminal back to the air handler, but also from the air handler and the BIS to the VAV box that allows control and override of temperatures from that VAV box. So to give you an idea of the actual structure, here's a wiring schematic that I drew from Siemens' presentation, and it might offer some visual clarity to what we're discussing. If we look at the actual room zone, the room VAV box with temperature airflow sensor, you can see that it is a device that regulates conditioned air to a space at a volume necessary to maintain a thermostat condition. It also is reading relative humidity potentially in the room. It also has a controller that will regulate a hot water valve to supply reheat to the VAV box during our cooler, shoulder seasons of the year, and also can actually regulate airflow based on carbon dioxide concentrations. Then that VAV box is hardwired to the room VAV box controller, which is also hardwired to the water valve as well. And it's from that controller that the various VAV algorithms are written. Then there's the central room operating mode and zone group. There's the air handler controller, and all of these devices are wired and connected and exchanging data between each other. And the mode of exchange or the language of exchange is BACnet protocol frequently. There are other protocols like LAN and Modbus, but what we see mostly today in our market is BACnet. The larger master group objects actually distribute and communicate the actual overall design parameters that each individual zone will take into account while maintaining its local discrete conditions. And then you have group member objects, such as terminal devices, VAV boxes, fan coil units, chill beams, that talk to individual group master objects or a zone group, which can be looked at in a VAV system as being an air handler. So these are all interconnected, exchanging information from the zone to the zone group and from the zone group to the zone, so that there's constant dialogue going on between these master and member objects. So the first thing that needs to be conditioned is the temperature set point. How do the guideline actually gives guidance on how to write zone temperature set points. In fact, it gives you the values that are displayed here. So the guidance in the guideline calls out that zone temperature initial set points can be specified by the designer in a number of ways. The most flexible way is to include them in each zone in variable air volume box schedules or in air handler schedules. I know at Veritech, I've actually written VAV schedules that actually include the values proposed by Guideline 36 to more facilitate the incorporation of those schedules into an engineer's specification. There's also outdoor airflow ventilation rate set points provided by the guideline, and it gives ventilation set points that can be specified by the designer in a number of ways. And the most flexible is to include them in each zone VAV box so that it can actually be measured how much outside air is being served and delivered to each zone to make sure that an indoor air quality level is being maintained. There are outdoor airflow ventilation set points, and the guideline leans on ASHRAE standard 62.1 as the standard to define how much outside air needs to be provided to each zone. And this is one of the elegant features of the guideline, is that if its sequences are followed, the guideline walks you right into standard compliance, 62.1, 90.1, etc. So it can take away from an engineering team a lot of the guesswork in hoping that their sequences fall within line with standard 90.1's energy efficiency guideline. So that's a very attractive feature about Guideline 36. It also shows, like for an example, if you have an occupied conference room, how the VAV box will actually control. This thermostat reads the temperature and sends it to the VAV controller for the damper to open to allow more airflow when a conference room loads up with occupants, and to throttle back and restrict airflow in the event the conference room is partially full or empty. So you can actually regulate the flow, airflow to the space so that the amount of airflow is appropriate to the demand of the zone, so energy is not being needlessly consumed to overcondition the space when it is not occupied. The general zone information also includes CO2 maximum concentrations. It says space CO2 sensors are used for demand control ventilation as required by the energy standards, such as Standard 90.1 in California Title 24, as well as for LEED. It then goes on to say that it is the designer's responsibility to determine the maximum CO2 differential between the zone and the ambient outdoor air condition, which Guideline 36 specifies to be as a common value of 400 parts per million. It also gives general zone information about zone dew point temperature. And for climate zones 0A, 1A, 2A, in other words, Phoenix, Arizona, Standard 90.1 requires supply air temperature reset be unimpeded by dehumidification controls, which means that your HVAC system in our geographic area has to maintain dehumidification regardless of the air temperature. So as dehumidification or humidity control becomes more and more apparent in maintaining good indoor air quality. It also goes on to say that dew point is used as the humidity variable rather than relative humidity. That was a change in 62.1 in 2019. So design engineers should be aware that they should consider looking at dew point as the proper humidity control value to design your, to look at your humidity levels within a building. The general zone information then goes on to VAV box design information, and it talks about VAV cooling only, VAV cooling with reheat, fan terminal units such as parallel boxes, series terminal boxes, etc. We just don't have time to go into those today at all. It also goes on to define what a zone group is that I've already referred to earlier in today's presentation. Zone scheduling groups or zone groups are sets of zones served by a single air handler that operate together for ease of scheduling and or in order to ensure sufficient load to maintain stable operation in the upstream system. It's not uncommon, especially for DX units, to struggle when there's low load. And so this language helps to overcome that challenge by making sure that at minimum load, there's adequate load to keep a DX unit online. There are zone group assignments. Zones and miscellaneous associated equipment must be assigned to the zone groups. Each zone served by a single air handler shall be its own zone group. Rooms occupied 24/7, such as computer rooms, networking closets, mechanical and electrical rooms, shall be their own assigned zone group. A zone group shall not span floors, and it shall not exceed 25,000 square feet. So the purpose of coming up with the concept of zone groups was to enhance the efficiency of the HVAC system, to provide stability and ensure AHUs have sufficient load to stay in operation, and for ease of scheduling as well. In order for all of these set points to be properly communicated and controlled through the BAS, the guideline offers a list of hardwire points for all the types of VAV devices that are available, and that actually writes out what points are listed as required, what points are actually to be included by the design team for applications as an A in the column. Points included as optional monitoring points shall have O values, etc. So it offers direction in the hardware list of what is to be, how these actual points are to be dealt with within the actual controls platform. And then there's section 5, the actual sequences of operation. The sequences in the sections 5.1.1 through 5.1.5 offers language pertaining to control loops when they are enabled and disabled. I should have said, there's a typo. What equipment action needs to occur when a control loop goes to neutral, when there are multiple outdoor air temperature sensors, and assigning authority. It goes on to discuss definitions such as proven, software point, software switch, etc., and how it applies to a sequence, when to use proportional, integral, and derivative control and associated guidance with that. It provides guidance to avoid abrupt changes in equipment operation, and then as well as set points, timers, and deadbands, etc. It also, in the sequence of operation in section 5.1, addresses alarms. The guidance recommends including at least the following requirements in the specification for the BAS graphical user interface: that all alarms shall include a time date stamp using the standalone control module, time and date. Each alarm can be configured in terms of level, latching, entry delay, exit deadband, etc. The sequence of operations, section 5, goes on to address variable frequency drive speed points. And then it goes on to actually address the efficiency of a system by addressing trim and response set point reset logic. It goes on to discuss equipment staging and rotation requests, air economizer high limits, damper valve positions, hierarchical alarm suppression, rather interesting concept I don't have my head around, time-based suppression, and outdoor air pollution mode. The sequences go into generic ventilation zones. A ventilation zone is a space or group of spaces served by one ventilation control device. For VAV systems, ventilation zones and thermal zones are one and the same. That will change with 100% outside air systems, but we're still waiting for language on that. There's language for zone minimum outdoor airflow rates and minimum airflow set points. For every zone that requires mechanical ventilation, the zone minimum outdoor airflows and set points shall be calculated depending on the governing standard and code authority. And then there's directions as well provided that identifies that an engineer needs to decide whether or not they're designing the standard 62.1, or if they're in California, they're going to be using California Title 24, and they have to use the appropriate language to meet either of those codes or those standards. So there are generic ventilation zones, and for compliance with the ventilation rate procedure of ASHRAE 62.1, this Section 5 is very clear on adopting 62.1's calculations for assigning the appropriate zone ventilation rate. VAV terminal units are also to determine the zone air distribution effectiveness required for each zone. Then there's language that speaks to that. There's also in the generic ventilation zone platform. Time average ventilation concept, which is actually the building up of a historicity of a performance of a system that can help override a problem zone that is being a predominant influencer in the operation of controls serving various zone rooms. There are generic thermal zones, and as the Section 5 goes on to state, the thermal zone in a VAV system is identical to a ventilation zone. The section applies to all single zone systems and subzones of air handling systems, such as VAV boxes and fan-powered boxes, as well as assigned set points for each zone, as we described earlier under the Section 3 section. So each zone shall have separate occupied, unoccupied heating and cooling set points as provided in Section 3 of the guideline. Generic thermal zones will also have assigned operating modes. There's going to be an occupied mode, warm-up mode, cool-down mode, setback mode, setup mode, and the guideline defines which of those modes need to be enabled when, depending on the time of day and occupancy. It goes on to define what a zone group is more thoroughly. Zone scheduling groups or zone groups are sets of zones served by a single air handler that operate together for ease of scheduling or in order to ensure sufficient load to maintain stable operation in the upstream equipment. It goes on to say that each system shall be broken into separate zone groups appropriately composed of a collection of one or more zones served by a single air handler. All zones in each zone group shall be in the same zone group operating mode when it is in a given mode, and each zone group shall be capable of having separate occupancy schedules and operating modes from other zone groups. So the modes of operation will be occupied, warm-up, cool-down, setback. Some are scheduled, some are assigned per the zone. And then it gives, when zones in one zone group are generating requests for different modes, a hierarchy of what is to be assumed authority of the various zones. There's language on chill water plants added in the 2021 edition. The plants sequences of operation assign plant enable and disable language. It goes on to cover the parameters for chiller plant enabling schedules and operator lockout, enable plant at lowest stage when plant has been disabled for 15 minutes, language when a disabled plant has been disabled for 15 minutes, and other guideline language for the chiller in the central plant. And then we're looking at central plant sequences to cover types of chillers, series or parallel chillers, centrifugal or positive displacement chillers, air-cooled or water-cooled, cooling tower staging, combination of chill water components. It is a very robust document. It also has now sequences of operation for hot water plants as well. That somewhat mirrors the chiller operation. That is to say, when is a boiler to be enabled, disabled, enable plant at the lowest stage when the plant has been disabled for at least 15 minutes, disable the plant when it has been enabled for at least 15 minutes, etc., etc. All of that language on hot water plants is involved in the guideline that we certainly don't have time to go into today. So the future of Guideline 36, in concluding remarks. The future of Guideline 36, where is it going? The guideline is moving into supporting pressurized fume hood laboratories. It is moving to provide language or sequences for dedicated outdoor air systems, 100% outside air systems that serve active or passive chill beams. Provide dedicated outdoor air systems that use passive radiant cooling and heating systems, perhaps arguably one of the most efficient design solutions in the market we have today. So concluding remarks, overcoming today's control challenges. The challenges we have today are that building controls are custom written and simplified for operational ease, difficulty in specified sequences having a common understanding by controls contractors and commissioning agents, as well as building service techs, sequences not written frequently with performance optimization in mind and are often simplified, a lack of standardized control results and system stability, delayed startup and commissioning in buildings, resulting in added construction costs, lack of building control sequencing, and a greater likelihood of poor indoor air quality. So the advantages of the guideline are common understanding between specifier, controls contractor, and commissioning agent, fault detection and predictive maintenance included so the owner can service equipment before catastrophic failure, offering greater stability. Sequences grounded in standard 62.1 and 90.1 to assure indoor air quality and energy efficiency. And adoption of the standardized sequences will support, in time, more common understanding of how buildings should operate more efficiently while creating healthier built environments. So, any questions?
So far, there are no questions in the chat, but we do have a couple comments.
Yes.
Pneumatics are still in use where there are buildings which have explosives inside, such as bomb factories.
Interesting.
So that is interesting. And
Thank you
then
for that.
Kruger put in here, from what I know about G36, the guideline recommends dynamically and continuously calculating the minimum CFM into a zone based on ventilation needs, so area and persons. ASHRAE personnel have suggested that the quickest significant improvement and ROI can result from this one change.
Wow. Thank you for that observation. That's good.
So if anybody has any questions, go ahead and type them in there. Feel free to also unmute yourself and just ask verbally. That was a lot of information, Dan.
It was. It's been a dense document to sift through. But it had to be done as we begin to, at Veritech, to become more aware of how to write sequences for our equipment and to have that dialogue with our engineering community. So this was is a first step of doing that and making that a reality. And we'll push forward more into this with the next webinar Wednesday on VAV systems.
Yeah. So what is the plan for including this into the rest of the year in the webinars?
We're going to keep the guideline in mind when we're actually addressing air design systems and continue to bring language when appropriate into control concepts regarding 100% outside air systems, VAV systems, and see what we can do to continue to re-engage with this language in the presentation so that we start making ourselves more familiar with how to apply it effectively and to offer more productive conversations with our manufacturers to make sure that we are addressing the sequence issue with our design engineering teams.
Perfect. I can't wait to hear the rest of your webinars this year. All right. Well, no questions have come in, so it's either really good or really bad. I'm guessing the first one. All right. Well, any more closing remarks?
No, thanks, Dan.
Thank you very much for joining us today.
Thanks
All
very
right,
much.
thank you, everybody. And there was some comments, Dan, that it was good. So it was not bad. It was good.
Oh, that's good.
Just digesting. All
Thank
right.
you.
See everybody next month.
Thank you.